Hi everybody, broadcasting the solutions to homework 5.1p taken from the 2003 exam. We're going to do this in two parts. Part 1 we're going to do A through C, and in part 2 I'm going to do D through E. Okay. Now I'm going to need as much space as I can on this one, so I'm going to go ahead and erase this. Okay. So I'm going to go through this. If I go a little fast, remember you can stop at any time and replay this video. So here we are, problem 2. A rigid 5-liter cylinder, that's volume, contains 2.5 grams of N2 and 28.0 grams of O2. So before we even start, there's a couple things that we want to realize about this. First of all, the container contains N2 and O2. So this is a mixed gas problem. Also, when you have grams in any type of gas problem, you traditionally want to convert these grams to moles. So if you converted 24.5 grams of N2 to moles, we could convert that to moles, and the 28.0 grams of O2 to moles. This is going to be 24 grams per every 1 mole. And we're going to get 0.875 moles of N2. And this is 32 grams of O2 per every 1 mole O2. And we're going to get 0.875 moles of O2. Okay, so we have moles of each now. And I want you to refer to these values when we do this problem. And these are actually going to come in a lot handy. They're going to come in handy as we do this problem. So let's do A. Calculate the total pressure in atmospheres of the gas at 298 Kelvin. All right. So we're going to go up here and do that right here. The first thing I want you to realize is they're asking for pressure. They don't give moles, but it is a mixed gas problem. So this is going to be 2A on the flow chart. So 2A says P total equals the sum of the two gases, and in this case that's nitrogen and oxygen. So it's P nitrogen plus P oxygen. Now what we're going to want to do here is do an individual P, V, nRT for each. So if we rearrange that, P equals nRT over V. So P equals nRT over V. We're going to do that for each. But what you're going to notice when you break this out is that temperature is the same for each. So we don't need to worry about that. R is the same for each. And V is the same for each. So really, N's are the only thing that change. So this can be collapsed into one equation. We can say that P total, since the only thing that's changing are the N's, we can say the N for N2 plus the N for O2 times R times T over V equals the total pressure. Okay? So when you plug in the 0.875 into this, you plug in the 298 Kelvin into this, we know R, and you plug in the 5 liters into this, you end up getting a pressure of, I believe it's 8 something, let's double check here, 8.56. atmospheres. Okay, so let me go over that again slowly. Okay, we have mixed gases, N2 and O2. Okay, they ask for the pressure. In the mixed gas category, you have two partial pressure equations, one which involves moles and one which involves just the sum of the individual pressures. We don't have mole values. We actually do here, but we don't have a total pressure to multiply it by. Okay, so we are going to know that the total pressure is the sum of the nitrogens and the oxygens. We could do two individual P equals nRTs over Vs, P equals nRTs over Vs to get the total pressure and add them up. But because the R, the T, and the V is constant with nitrogen and oxygen, we can do 1 P equals nRT over V and just sum up the mole values. Okay. And that's what we did here. We got 8.56 atmospheres. That's done. In this one, it says the temperature of the gas mixture in the cylinder is decreased to 280 Kelvin. Calculate each of the following. So I'm going to draw a little picture over here to help you out. We have this cylinder that's 5 liters. And inside the cylinder, we have 0.875 moles of N2 and 0.875 moles of O2. Okay, inside this rigid cylinder. Okay, so in this first problem, it says calculate the mole fraction of N2 in the cylinder. So the mole fraction is simply the moles of N2 over total moles. And you'll see this in the equation. Look at equation 2b. You'll see this multiplied by the total moles often. So it's just basically the fraction of moles inside this container right here. So even if the pressure has been dropped to 280, since it's sealed, these moles are not leaving. These particles are just going to have a lower kinetic energy, and they're probably going to occupy, be bouncing off this container with a smaller pressure and might ultimately take up less space. Nothing is escaping this. Okay? So the mole fraction is not going to change even though the temperature is decreased. So moles of N2, right there, 0.875. Total moles, 1.750. So 0.50 equals the mole fraction. Half of the moles are N2, and that's really what this refers to. Half of moles equal N2. That's what the mole fraction is referring to. Okay, calculate the partial pressure in atmospheres of nitrogen. So I'm going to go down here and do that. So partial pressure, we're in column 2. And we actually now have moles, and we have the temperature, 280 Kelvin. So moles of nitrogen are N2, and total moles are 1.750. So we're going to use the partial pressure equation. Partial pressure of nitrogen equals moles of nitrogen divided by total moles multiplied by P total. Okay. So let's plug this in. Pressure nitrogen equals the mole fraction. That's really what this is. Did we calculate that already? I believe we did. There it is, 0.50. So 0.50 multiplied by the total pressure. So we know that this is going to be an equation that comes out to nRT over V, and the total moles here, we can do that because we know this equation is 1.750 and multiplied by 0.0821 multiplied by the new temperature, 280 Kelvin, divided by the volume, which is 5 liters. Okay, so basically half of the total pressure is going to be caused by the nitrogen because the mole fraction is half. And when you do that all out, I believe we're going to get a pressure of 4 atmospheres.